Hello and welcome to BioRules video lessons. We've been talking about diffusion and transport across the membrane. So today we are going to be talking about a very special kind of diffusion called osmosis. But for us to understand osmosis, you need to go back, just to make a quick revision that what you just learned about diffusion. But in this case here, I've put there in between the two sides of this container a partially permeable membrane. Or it's a partial permeable membrane, also known as selectively permeable membrane, a membrane that allows some particles to move through but not others. In this example here, I am allowing these blue dots, for example, if it's water, for it to move through. As a result, the particles are going to bounce all over the place, and as a result, because we have the same amount of particles to one side and to the other, they end up moving equally. So if this was water, for example, the particles would move to the left, they will move to the right, they will move all over the place, but there would be no change in the concentration, in the number of molecules of water in both sides, because they have a net movement of zero. Okay? So if water particles are allowed through, they end up to move to one side as much as they move to the other. In this case, we say zero net movement, no liquid movement, no movement as a result at all. Although the particles are moving, they move the same amount to one side as they do to the other side. Okay. Now let's complicate a little bit. I don't have only water, the blue dots. Now I have here some small particles that are added to one side. What do we expect to happen? So we saw this before in diffusions class, that these particles are going to be bouncing around, and as a result, they'll have a tendency on moving more to the right than they move back to the left. So if they are allowed to diffuse, they will diffuse, no use of energy, from left to right. Simple, we just saw that. However, now I will complicate it a little bit more, and now we're going to be talking about osmosis. What happens if we have a partially permeable membrane, we have a solvent that is allowed to move through, but we have solutes, the particles, that are not allowed through. As a result, I am going, with this partially permeable membrane, to have the solvent moving around. I have the solutes trying to move around, but as a result, what will happen is that, let me go slowly because this was too fast probably. What will happen is this. I will have water molecules moving to the right. I will have water molecules moving to the left. Okay, so far, looks like the solutes not diffusing, but the water is diffusing. Okay, what's new? What will happen here is that sometimes the water molecules that are on the left, they will try to go, they are in the direction to go to the other side, but they end up bouncing in the solutes that are on the left. So they don't manage to cross through. And then we have one on the right that they're moving freely, there's no solute over there, they manage to pass to the left. And then there's another one, look, it was going the right direction, it bounced again, it doesn't manage to go to the right, they stay on the left. And on the left, on the right, there's one that just passed through freely. So this here is going to be happening, with particles on the left interacting with the solute, the solvent interacts with the solute, and end up staying there for a little bit longer, not manage to pass to the other side, while on the right you don't have solute, you only have solvent, you only have water, so the water particles, they can move freely, and they end up moving to the left as freely as they could. So as a result, you have a net movement. Let me put this here in a very dark purple. Here we have a net movement going to the left in this example here, because we have more water molecules moving to the left than we had going to the right. So if the solute's not allowed through, but the solvent is, the solvent will cross to both sides, but they will end up moving more in the direction where you have more solute, because they take longer to move back to the other side. So as a result, they tend to try to equalize the concentration. Of course, they're not thinking, they're not trying, but the idea of osmosis is that when the solvent diffuses, they diffuse from low to high solute concentration, and as a result, they end up quite trying to equalize concentration. So let's take a look on that, thinking another example. Okay, this one, let's make it a little bit more palpable. Think that you have two adjacent rooms. In these rooms, you have a door between them, and we put 20 kids in each of the sides, and we let them run at will. They can run whatever they want, they do what they do, kids know they run around. So we have kids, and they are going to be quite spread, right? So if you let, they'll go over there. We have more kids on the left than we have on the right, so they tend to move more to the right. Sometimes some move back to the left, but as an overall result, we have diffusion. We have a net movement that goes more from the left to the right until it equalizes both sides. So this here is diffusion. You saw it before. So the kids will end up balancing both sides. But what will happen, if instead of having just the kids, which in this case is representing the solvent, the water, what happens? What happens if we have? Okay, a bounce here, there. Okay. What happens if we do have the same situation, but now we have a table in one of the sides? So basically, now this is what was happening there. So very good, they are balanced over there. But what happens now if one of the rooms I put desks, especially if I put desks containing toys? Kids love toys, right? So what will happen here? In the non-furnished room, the kids will bounce freely and at will. So they will end up eventually moving to the left room. But on the right, if the kids allow through, it also moves to the right room. Once eventually it moves to the right room. But as a result, sorry again, I have to go back here. Here, what will happen then? That kids hold the desks, they hold kids around for a while. So what we see here is that those desks, they are going to keep the kids around the left side for a little bit more often than the kids on the right side that can move freely. So as a result, kids are going to end up moving more to the left than kids move to the right. They don't want to move there, but they interact with the tables, and by interacting with the table, they end up moving less from the left to the right than they move from the right to the left. The natural tendency then is to increase the number of kids on the left side, so the water, the kids are representing water here, will tend to try to equalize the concentration of the solutes. Okay, just to give you another clear example, here we have a beaker divided by a selectively permeable membrane, a partially permeable membrane, and I have sugar molecules. What do you think is going to be happening? So in this case, on the left we have a high sugar concentration, on the right you have a low sugar concentration. Sugar is not allowed to pass through this selective permeable membrane, so what will happen is that water will pass to both sides, but the water is interacting more with sugars on the left than they interact in the right, so they will have a tendency on moving more to the left. And this movement is so powerful, osmosis is such a strong force that it beats gravity. It actually is capable of moving water to the left even against the acceleration of gravity that tends to push this down on the left. So yes, osmosis is a very powerful movement. I very strongly advise you to watch this animation. Okay, this will make things very clear for you to see things animate in front of you, for you to understand osmosis. And after you watch it, or you can watch also in the end of my video, but get the QR codes here now so you can take a look on the video later. Okay, and now 3 examples for you, is stating for you a new nomenclature. On the left, we have something called the hypotonic solution. Tonic is concentration. So hypotonic solution means a low concentration. Hypo means low. Hypoglycemia, low glucose. So hypotonic solution, low concentration solution. As a tendency, you can see in this diagram that the red blood cell was added, and we have 4 arrows of water moving in and 2 arrows of water moving out, because the hypotonic solution has a lower concentration comparing to the cytoplasm of the cell. It's low concentration. So the tendency is for these cells to gain water more than they lose, so they have a net gain of water, so the cells swell, and they may even swell so much that they may even bust. Okay. In the middle, we have a hypertonic solution. So hypermarkets means high, very high, a lot of concentration. So high concentration solution. The solution has a higher concentration than the cytoplasm of the cell. So as a result, you have more water than solvent inside compared to the outside, where you have less water to the solvent ratio over there. So as a tendency, you see in this diagram that we have 4 arrows of water moving outside, then only 2 arrows moving to inside. So as a result, there is a net loss of water, and the cells are going to be shrinking. Okay? And on the right, we have an isotonic solution. Isotonic means same concentration. By the way, yes, this is the name of Gatorade or other chemicals that are supposed to have the same concentration of our body fluids. They have same concentration of our blood and our sweat. So the tendency here, if this concentration is the same, is for water to move out and in the same proportion. So there's no net loss or gain of water. Okay? I hope you got the idea. If you didn't, play back again this part so you understand what's a hypotonic, what's a hypertonic, and what's an isotonic solution. Here I have a diagram with a question for you. What do you think are the concentration of the situations A, B, and C, taking into consideration that this is one of each with red blood cells? I'll start by the C. What do you think C is? If you have to think, pause the video and then you come back. Okay, in order to unpause the video or you thought very quickly, what is the concentration of solution C? If you said hypotonic, you said it right. Because as you can see here, these red blood cells are swollen, meaning that water is moving in much more than water is moving out. So as a result, water is moving in because you have much more water outside, you have much more solutes into the inside, so the water tends to go to the high solute concentration, equalizing. So this here, therefore, it is hypertonic solution. What about B? Pause your video, think a little bit, and then you come back. Now that you unpause the video, what do we see here? These star-shaped cells, they seems that these cells have shrunken, so seems that they had a net movement of water going outside. So their water is going outside is because outside has more solute than the cytoplasm inside. So this solution then, oh sorry, I made a mistake over there. Sorry, I'll have to fix this again. I hate when I do that in a video. That one is not hyper, this is hypo. Oh, why didn't you correct me? So hypotonic, because you have here outside a low concentration, then it enters in there. And then here we have a hypertonic solution because the water is moving outside. Water moves now to the place where you have a higher solute concentration, so hypertonic. Some of them didn't move much, so this is hypertonic, but some of the cells are resisting this movement. And this here, option A, what do you think? Pause your video and come back to tell me what it is. Okay, now that you came back, what we have here? Most cells, they didn't change much, so apparently water is moving in and out in a similar situation. Although some of this here seems to have lost a little bit of water Here, this seems to have lost a little bit of water. So in this case, I would say that this is isotonic or slightly a hypertonic solution, because some of them shrunk a little bit, but this is more toward the isotonic. Okay, I know this is not so trivial, so please watch the video that I put before, go for your book, try to get the idea, and I'll talk to you in class to see if you still have doubts and for us to solve and give more examples. Okay, I hope you had fun. Do the quiz now, and I'll see you in class.